Hello, I'm Jacob Kravits. I worked on this project with Joseph Kasprazik, Kyrie Baker, and Kostas Andriadis. My goal today is to motivate the need for a multi-objective approach to machine learning hyperparameter tuning. To demonstrate this, I will be discussing the problem of classifying dam hazard potential. But I want you to keep in mind that the methods that I am motivating are generic to any sort of machine learning classification problem. So dams do not fail often, but when they do, it can be catastrophic. So let's look at some recent catastrophic dam failure examples. Here's a picture from the Brumadinho Dam failure, which happened last year. That was a tailings dam in Brazil that failed and killed nearly 270 people. This is a picture from the Tuware Dam failure in India, which flooded 7 villages and killed almost 20 people. And a recent example from earlier this year is the Edenville and Stanford Dam failure in Michigan, United States, which forced 10,000 residents to be evacuated during the ongoing COVID pandemic and caused an estimated $175 million in damage. So one way that's typically used to allocate resources to dams is by classifying a dam's hazard potential. When classifying dam hazard potential, a classifier needs to use human judgment to ask if this dam fails, what would happen. So if nothing major would happen, maybe some small sediment deposits, it's considered a low hazard potential. There are economic damages from the dam failure. It would be considered a significant hazard potential. And if there's probable human death, it's considered a high hazard potential. Now, for some large-scale reservoir systems, this question is fairly straightforward. However, for some smaller systems, this question is not so trivial. So consider the Pawtucket Dam in Lowell, Massachusetts, in the United States. It's only about 16 feet tall, stores roughly 4,500 acre-feet of water, but it's right upstream from downtown Lowell, which has a population of just over 100,000 people, houses a major university that's located right on the river. And so the question of whether or not this is a high hazard potential dam is not exactly straightforward. The good news is that we have tools to simulate these dam failures and dam losses, but unfortunately these tools take time and expertise to run. And that fact is particularly problematic because there is a lack of resources for classifying dams' hazard potential. Additionally, hazard creep makes this problem even harder because the hazard classification of dams changes over time as people settle in new locations. So to summarize the problem, dam hazard potential needs to be assessed continually, consistently, and across large spatial extents, but that is difficult under the current system. The good news is that there is a vast amount of data that exists on dams in the existing hazard potential classifications. And so we can reframe this problem as a traditional data classification problem. Recent work has applied machine learning to solve this problem. And we see the features that they use to predict dam hazard. They make sense. Dam height, dam length, the capacity of the reservoir. But let's reflect on that Pawtucket Dam system we saw a few slides back. One of the key characteristics of that system that made that problem not so straightforward was the location of that system relative to that urban downtown. So we asked ourselves, are there any additional spatial features that we can add to this problem that really capture those inherent spatial aspects? So we dove into the literature and found these additional features. And a lot of these are logical choices for classifying dam hazard, as we have defined it a few slides ago, like the downstream population. But these features aren't deterministically known, so we need some sort of model to estimate them. So let's start with the data that drives our spatial feature model. We know H, the height of the dams. We know the locations of the dams. We know the surrounding topography of the dams. And we also know many census block level data, such as population in each census block, or the average value of buildings in each census block. And the overall goal of this model is to take zonal statistics of these spatial data sets such that every spatial feature will have one numerical value associated with it for every dam. One problem is that the state methodologies are not consistent in how they emphasize these spatial aspects. Some states really emphasize the downstream impacts of a dam failure, while others take a simple proximity perspective. So we propose a two-parameter model, one parameter being n length, the other parameter being n width, that reflects this dichotomy. So let's step through the model. First, we compute a drainage from each dam location that's similar to the gradient descent problem in calculus. Now recall the goal of this model is to compute a zonal statistics, so we need a zone over which to compute that statistic. So we buffer that drain based on the n length and n width value. The width of that buffer is determined by n width. The length is determined by n length. You'll see that we're controlling for the size of the dams by including the dam's height. That eliminates the need to have one of these n length and n width values for every dam. The illustration here is for a system that has a large n length value and a small n width value. Next, we take a zonal statistic of our original data sets over that predictor area that we just computed. This process is then repeated for every dam, and we see the outcome of this model is a set of spatial feature values for every dam. Now, to classify those features, we use a random forest. And to jog your memory, a random forest is an ensemble of individual decision trees, with each decision tree having its own classification outcome. And then majority voting occurs to get a final outcome. Now, things like the number of trees in the forest, the maximum depth of any tree, those are all controlled by hyperparameters. Those are independent of the training process. And so these are the hyperparameters that we focused on for this study. And so let's recap. We have these 7 hyperparameters that we need to tune. We also have those 2 spatial model parameters from the last slide. And we could use some expert knowledge to just guess these parameters, and our model would work. But if we really want to make sure that our model is optimal, we need some way to quantitatively tell us how good any of these sets of parameters are. And we want to quantify model performance using objectives. A logical and very common objective is accuracy. That would be the ratio of correct classifications to total classifications. It would be the diagonal on this confusion matrix that I've shown in the top right corner. But let's think about those false positive cases. Those are dams that are truly high hazard, that our model classifies them as not high hazard. And that's a direct threat to public safety, right? That may mean that those high hazard dams won't receive adequate funding. You could also consider those false negative classifications. That may mean that we're falsely scaring people. And so we can actually select different objectives like false positive rate and true positive rate that directly capture those misclassifications. We can also select more holistic objectives like area under receive operator characteristic curve, which capture model performance over a variety of classification thresholds. And the goal of formulating the problem in this multi-objective framework is that we want to explore trade-off among these objectives. And to do that, we are going to use a multi-objective evolutionary algorithm, or an MOEA. For those of you who don't know much about MOEAs, they're a class of genetic algorithms that evolve sets of non-dominated solutions to multi-objective problems. And to refresh, a non-dominated set of parameters is one whose performance is better than another set's in at least one objective, but no parameterization's performance is better than another in all objectives. And as we'll see, this is a highly iterative process. So first, the MOEA, we're using the Borg MOEA, suggests sets of hyperparameters and spatial parameters. These spatial parameters are then run through the spatial features model. You'll see that for this computational experiment, we are using dam data from Massachusetts, United States. Once we have the dam features, we use a random forest to classify them. We're also using a 5-fold cross-validation as not to optimize our model to any one specific split in the data. And this produces a set of 4 objective values. These 4 objective values then inform the MOEA's next choice of hyperparameters and spatial parameters through an auto-adaptive framework. We ran our search for 100,000 iterations, which we found was sufficient based on separate analysis of the hypervolume for this search. The outcome of this search are sets of non-dominated hyper and spatial parameters, as well as their objective values. And it's helpful to plot these objective values on a parallel axis plot, as I've done here. An ideal solution would be one that ran across the bottom of this plot. The colors of these solutions here are also redundant with the false positive rate objective. Okay, so what are some of the big takeaways? We can see the severity of the trade-off between accuracy and false positive rate. Physically, this means that maximizing correct classification comes at the cost of wrongly classifying high-hazard dams. Accuracy and true positive rate are complementary, so including them both generally redundant. We also see that extreme low and high accuracy results tended to have lower area under receive operator characteristic curve value. This makes sense as those solutions highly optimized to a single classification threshold may not do as well over all thresholds. And we do see that we gain new solutions by including this objective. So now as an analyst, we can query these solutions based on our preferences to the problem. Perhaps you have a minimum accuracy criteria or a maximum false positive rate criteria. And we can select a single solution in the context of a full set while expressing a preference. Ultimately, this gives you greater justification for your spatial and hyperparameter values. So what are some broader takeaways from this work? We developed a geospatial model to estimate new features for the dam hazard potential classification problem. We saw that a multi-objective approach to hyperparameter tuning allowed us to explore objectives that capture different misclassification types. And if we circle back to the beginning of this presentation, we saw that dam failures can be catastrophic. It's bad if dams fail unexpectedly, but it's also bad to falsely scare people. There are clearly competing values, so this classification problem is inherently multi-objective. We have seen that machine learning algorithms offer a very powerful tool to streamline the way that we assess hazard potential. And so if the problem is multi-objective, I believe that the way that we optimize these machine learning algorithms must also be multi-objective. We recently submitted this work to the Journal of Water Resources Planning and Management. I would like to thank these people and all of you for listening to this presentation.